I want to talk about repairs inside the refrigerant system, but specifically compressors, because of the system, of the repairs that you make, the compressor is going to be the most complicated. It's going to be the one that, well, reversing valves more, but you know, how many reversing valves actually fail? You know what I mean?
Very few, not very few.
Yeah, very few, and usually when they do fail, you put it in and you realize it's with the compressor. So I just want to hit on a couple things, and then I'm going to let Ty riff while I go take care of business. So here's a really common one, first and foremost, and that is the whole capacitor versus contactor thing. So you've got your C, you've got your fan, and you've got your herm, okay? So does everybody know what connects to herm on a compressor? So we got a compressor here. We've got common, we've got start, we've got run. Actually, is that no? That's not how they are. What is the orientation? It is CSR, but is it CSR? I think it's.
There's different brands that have different ones.
I know, but there is the most common one. I think it's like this. We'll do
Common's
that.
the C.
And all right, so our herm goes to which one of these terminals?
Star one. Star.
Goes to start. That's we started there because that's the easy one, right? Okay, so herm goes to start. Now again, for those of you who are newer, you just take a picture, right? So that way you can remember when you go to wire. That's a good idea. You're a little nervous, take pictures. That's helpful. But you can memorize this. This is not that difficult. All right, now where does run go?
Same leg that powers the capacitor.
The same leg that powers the capacitor. Okay, so let's say we got a contactor. I don't know why I'm putting X's on the. I guess that's important to me for some reason.
Okay.
Okay, so we've got here, and we're going to say that this side is going to common. Well, actually, I shouldn't say this yet. So we've got these here, and this is going to be. We're going to have black wires going on this side, and then we're going to have other colors on this side. All right, usually yellow on carrier. So what feeds this terminal on your capacitor?
The one was constantly powered there.
Is it the black side? No, it is not. It is this side here. So you're going to have wires that go here, right? Now, your run is going to be powered from either going to this C on the capacitor or all the way back over here on the contactor. Okay? It is not, and this is where it gets weird because we say common, we call this common, and we call this common. Well, this common connects to the run side. This common here goes to the black side, the other common. The point is, and this is all you really have to remember, is that compressor common and capacitor common ain't the same common. Right? Capacitor common goes to the run side. Compressor common goes to the black side of the capacitor opposite from the run side. Anybody have any questions about that? It's fairly, again, you should all be able to unwire and wire a capacitor, a compressor, and a contactor in your sleep. If you're not, well then go through a used crappy unit and just do it a couple times. Or next time you do it, work through it in your mind.
There's also a handy picture on the inside that tells you where.
There's a handy picture on the inside called a wiring diagram. HVAC school, we have specific illustrations that show this and talk through this. But I just want to make sure everybody knew this, okay? Ty, you can go through this, or also the where you charge the refrigerant on a system that's got no refrigerant in it.
Looking at the compressor, I find electricity quite shocking. Alright, so we have those terminals, and inside the compressor there's sets of windings. That I should have brought the windings in. But when you have your run winding, it's a large, shorter winding, and it connects over here. And then you have another winding called the start winding, and it's a long, skinny wire, and it goes over here. And instead of having two wires going back to the contactor, we can just put them together. All right, so after we do work in the run winding, then we do work in the start winding, they're both going to the opposite side, so they share something in common. Yes, that's it. I couldn't think of it. Yes, they have something in common. So it's not so much that all commons have anything in common I got friends that are Republicans and I got friends that are Democrats, and they both have things in common, but they do not cross each other. I promise you that. So we have the compressor common because they share that one wire coming out. That's all that means. But this is the start winding, and this is the run winding. So far, so good? Okay, so we talked about, Ryan talked about the capacitor. And so the cool thing is, like, when you can memorize the wires, but when you get one that's a different color, then it becomes like, it makes you think. And then those little habits, whoops, let me do it like, yep, those little habits become like at the window. Like you memorize the wires, you always work in a carrier, this, and that. But what happens when I change the wire on you and you have to like, oh man, different brand, or somebody else changed the wire, and we get a different type of compressor and it's a different wire. Then we change things. So in this example here, so I'm just gonna put this back to the contactor. So which side powers the run?
Our yellow right side.
I don't have a yellow wire.
Our right side of the contactor, that's not our main.
This side?
That's going to be compressor. The other side.
This side? This side goes to run?
Yeah,
Are you sure?
I'm not sure anymore.
Yes, it does. You were right. Don't second guess yourself. That's correct. Yes. That's exactly how it goes. So what we have is the difference between these 2 points is 240 volts. There's a lot of potential difference. So electricity is flowing through the run capacitor back home. Now we say this, we run to work and we see common come home to the opposite side, but it's alternating current. So it's changing direction 60 times per second. 60 times a second. Isn't that cool? Like, that's fast. Can you count 60 times in a second? Let's try it.
What is it?
So it's going back and forth, and it's energizing the main windings that keeping that motor running. We'll also do the start winding to assist it, to make it more energy efficient. So what we're going to do is put ourselves in here a capacitor, a capacitator. All right, so here's just a single capacitor. Which side of that capacitor is common? Doesn't matter. It doesn't matter. It doesn't matter because it's just simply 2 plates. If you look inside of a capacitor, you'll see 2 plates. Kind of, but they're really rolled up and it doesn't look like that. But it's simply 2 plates. Just stores electrons. So what's happening is this run winding is powering the main motor. But 1/60th of a second, this run winding, as that motor AC current goes the other way, we have a magnet, and that magnet is pushing through this coil of wire. What happens when we send a magnet through a coil of wire? Anybody know?
Yeah, sorry.
It will charge. Have you seen those shake lights? You have a magnet and you shake it back and forth, and you send a magnet back and forth through a coil of wire. You seen those? I have one in the box out there. Go get it if you want. But you shake it. If you have one of those hand crank flashlights or the old radios, you simply have a magnet and you're sending it through a coil of wire. You're generating electricity. The shake light does the same thing. It looks kind of weird and creepy, but yeah, if you're sending a magnet through a coil of wire, you generate electricity. If I send electricity through a coil of wire, what do I get? A magnet, electromagnet, a solenoid. Right? We use solenoids all the time. So what's happening is 1/60th of a second, this start winding actually becomes a generator. It adds voltage to the motor. It increases the voltage. So we got 240 volts here and here. 1/60th of a second, that motor that's spinning inside of here turns this into a generator. And guess what happens to the voltage? Yes, it goes up. That's exactly right. It goes up. The voltage goes up. So the voltage on the start winding is going to be higher because it's back electromagnetic force. We're increasing the voltage. That voltage is back electromagnetic force. So that voltage comes over here and pushes the electrons into this plate. The size of this plate determines how many electrons it can store. If we have a smaller capacitor, it stores less electrons. But if we have a big capacitor, it stores a whole lot of electrons. But we can't, because electrons are magnetic, I can't push electrons over here because there's electrons trapped here and I can only get so many in. You ever try to put 2 magnets together? So they push apart, you can't get it to happen. So what we need is a path for the electrons on this plate to go away. Now, which side should I connect this to? Should I put it on this side or this side? This wire here. Here?
Your
Or
common
here?
side.
The what side?
Your common side on the right.
You can't be on the same. It's gonna be the other side.
The other side over here?
No.
Over here?
Yeah.
Here?
It doesn't matter, I guess.
Or here?
Up top.
Only one person? What do you guys think? What's happening? What would happen if I put it right here on the same side here? What would happen if I took this electrical prong right here? Something would unplug. If I unplug this, how many prongs are there on here? 2. What happens if I squeeze them and put both of them together and put it in the same side of the outlet? Would it pop?
Actually, no. Up here.
What do you think would happen?
Nothing.
Nothing would happen. Are you sure?
Yeah.
It would kill the item.
No,
Kill
no,
the
nothing will happen
current.
because you need to have potential difference to have current. So.
Yes! That's correct! Nothing would happen. If I put both of these terminals together on one side, nothing would happen because there's no potential difference. If I was to hover in the air and I was to stick a fork in just one of these outlets, what would happen to me?
That's good.
Nothing. Nothing would happen because it's only on one side. What if I took 2 forks on one side of the plug outlet? Just one side, 2 forks on one side of the plug outlet. What would happen to me?
Still.
Nothing. What if I took 15 knives and tried to shove them in the same side of this plug outlet? What would happen to me? Nothing. 15 of them. I could have 100 if I could get it to fit, and nothing would happen because it's the same side. Now, what happens if I took and put one on the other side? Then I'm getting shot because now there's a potential difference. There's voltage. Or if I'm standing on the floor and I, depending on what kind of shoes I have, maybe I'm standing in the salt water and I touch one, now there's a potential difference. If that bird is on that wire up there, he's on the same wire. They don't get shocked. But what happens if they go and peck on the other wire or something wood on there? Or not the wood, but the ground wire on the pole. What happens to that bird then?
Thanksgiving.
Boom! Right? It's quick. There's now potential difference. Now there's a path, there's a flow of electricity. So in this capacitor, if I installed it here on this side, it's the same wire. What would happen? Nothing. Nothing would happen at all. Would it burn anything up? It'd be harder to run money, but it wouldn't burn anything up because it's on the same side. Nothing could happen. For me to have an actual path, I need it to be on the opposite side. So now what's happening, the run winding is carrying most of the work. 1/60th of a second, this becomes a generator. It's pushing electrons into this plate. From here, this plate pushes electrons back over to here, and we're storing electrons. 1/60th of a second later, what happens to the AC current? It goes the other way. So now the electrons are flowing the opposite direction. So now say electrons are flowing this way. So this capacitor, AC current changes, all these electrons that we had stored, guess where they're going? They're going out. They're going away. They're going the other way. So now the electrons, the flow, the amperage is going this way, and it's helping that motor turn. Store electrons, discharge electrons. Store electrons, discharge electrons. Electrons are just going back and forth. They're going into this and away. How many electrons do you think go from one side of the capacitor to the other? How many electrons? Which is part of an atom. So if we actually have an atom, you have neutrals and protons, neutrons and protons, and then floating on the outside you have these electrons. And you have, they're like orbiting, like solar systems, and you have different ones, different made up, but copper has one electron over here by itself, a valence electron, and we can knock that sucker off with another one. We hit one, it knocks that one knocks the next one, knocks the next one, but we can take all those electrons and we store them up over here. But how many electrons go from this side of the capacitor to that side of the capacitor?
2.
2. Okay, what do you guys think? Is that correct? 1,000? Okay, I like that. I like that. 1,000. Okay, what else? Who else has an answer? What do you think? What do you think? How many's going across?
Across?
I don't think so. It's just, you say it. It's like back and forth.
It is back and forth. But how many's going from one side to the other through the capacitor?
Through the capacitor.
Yep.
just feel like it'll be constant. I don't know. I don't want to say infinite, but it'll be a lot.
What do you think?
On start, like on startup, like one time?
Ooh, is there a difference between startup and while it's running? Is the size of the capacitor going to change it? What do you think?
I think the size of the capacitor changes it. I don't know.
I don't know. That is the answer. That's the most honest answer. I don't know. You know what? Do you guys know what I don't know? I don't know what I don't know.
Yeah.
0 electrons go from one side of the capacitor to the other. No matter how big it is, how small it is on startup, no matter what, 0 electrons go from one side to the other. There are plates, and that plates keep them separate. The electrons do not pass from one side to the other unless the capacitor is bad. If the capacitor goes bad, then you have electrons flowing through it, right? Then you have an issue. We shouldn't have any electrons flowing from one side, no matter how big or how small it is. So it's like pretty cool. So now it's simple. So now we understand like why they have to be on the opposite side. So the same side, the same leg that powers the run winding, and powers is loosely because it's alternating current, the same leg that powers the run winding also powers the capacitor. That term is loosely because we know it's just electrons going back and forth, back and forth. But what happens if I have me another motor and I have another run winding here, and then I have me another winding that's a start winding, a lot smaller wire there. I'm going to need another capacitor for this, right? So I'm going to put me another capacitor here, a nice small little capacitor. What leg powers the run winding? This leg, this leg, this leg, this leg, this leg. Where should I get power to power the run winding of this little fade motor?
The opposite side.
Over here?
Yeah.
Everybody agree?
Um,
So I should come from over here like this,
uh-huh.
okay? And then where does this side go? Where does this side go?
Nobody knows that anymore. Yeah, nobody.
I know it, and that's what makes it good. Is I know it. I'm laughing inside. Like I'm seeing Trebek pre-cancer. Right?
Oh, whoa. Whoa.
Yeah,
Wow.
start quick. Too soon.
Nice.
Yeah. Well, which leg powered the run winding on this motor? This one or this one? This one. So if this leg powered the run winding here, wouldn't it be nice if we just kept it consistent and had it powered that same one? So can I use this leg instead to make it simpler?
Sure.
Sure, let's do that. We'll talk about why here in a minute. So if this one ran to work, what is this one going to do? See common come home to the opposite leg. Boom. We're almost there. But now we have to power that start winding. Where's the start winding going to connect to? A capacitor. And this is my beautiful real life 3D image of a capacitor, right? So we're going to connect this wire to. Boom, we're going to connect to the capacitor. But if I have only one side connected, the electromagnetism, I can't push any electrons in because this side has electrons that aren't moving out. So I can't push any electrons into the capacitor. So what do we got to do?
Put a jumper between.
Well, I could power it from all the way over here, right? Or what do you say? Put a jumper here. Why would that matter? Why can I do that? Why don't I have to go all the way back over here?
It's the same path.
It's the same path. It's the same leg. I could literally, if I wanted, cut the wire here, and it would look really horrible to do not do this, but you could electronically cut the wire here and put it there if you wanted. It would be completely impractical, but you could take all the run windings here and then back over there because it's the same entire leg. Don't do that, but I'm just electronically, right? So now we've put these two capacitors, we've connected a terminal. Do these two capacitors have anything in common with each other? Yeah, this is now a common wire. They now have something in common. They're like, hey, like we're different, bro, but like we have something in common. We're sharing the same leg that powers the run winding. They have something in common. Now, is the commons of this capacitor the same as the commons of this capacitor? No! No! Completely not the same at all. What would happen if I then powered this wire here from this leg? if I took a wire from here and tried to power this common? It'd be coming back to the same leg, right?
Gotcha, yeah.
So would it work? So if we put the commons together, would it work? No. So just because it has, and the way I teach it is C for capacitor stands for power in capacitor. I don't even teach it as common because it causes confusion. But at some point in time, they gotta learn that it's common because they have something in common. Now here we can see this jumper wire, but if I put both these capacitors in one cool little can, and I name this one Herm for hermetically sealed compressor, and I name this one Fan for the fan motor, and then what is this one going to be, you think?
Power.
C, power for capacitor, yes! Because inside there's a little jumper wire, sort of, and it's simply sharing. They have something in common, but it's the opposite of the commons over here. So we have to have a load before we go to the other side. Okay? Does that make sense? Yeah, maybe, maybe not. Need more coffee? Boring?
So it's important because this is one of these cases that the smarter you think you are, the more you think you've got it, the less you're likely to take a picture or refer to the wiring diagram, and the more you're likely to just start smacking things together. And then, oh, this isn't working. Bad compressor out of the box, right? It's an error that a more experienced technician who feels like they've got it is going to make. Until you get to the point that's like, oh, I really don't understand. Like, again, like Ty just explained how capacitors work. It's one of the things that Ty and I have both spent the most time talking to people about because they just fundamentally do not understand how capacitors work. But the vast majority of super experienced technicians who don't think they have anything to learn anymore have no idea how they actually work. Hard start kits. How does a hard start kit work? What does it actually do? Oh, it adds a boost to the compressor. Sure. No, it's much more. There's much more to know there, and knowing it actually makes you a better technician. Because then, when you see a failure on the start winding, you now know, hey, start winding failure, almost always due to start gear. Almost always, because it's this thin little winding. And if you put too big of a run capacitor, or you put a hard start kit on, and the potential relay fails, or whatever, that's what causes that start winding to fail. Things like that, right? So now you know where to look because you actually understand how it works. And that's not a criticism. None of this is a criticism. This should make work more fun, right? Understanding what you're doing and why the things happen that they happen, it's an endless pursuit of understanding.
So what would happen if I put in a capacitor with larger plates? What happened to the electrons?
It can store more.
Yes! It can store more! That's exactly right! You can store more electrons. So if I put more, what if I put two capacitors here in parallel, like train tracks? What's happening to the size of that capacitor? It's bigger! Guess what it can hold?
More.
More electrons! So when the alternating current changes direction and goes the other way, do I have more electrons going to that wire? What does that do to the amperage?
Increase.
It increases. We're having more flow of electrons. So if I put a capacitor that's too big, what's going to happen to this winding right here?
Melty.
Could melt. It's going to overheat. There's insulation on that wire. It looks like copper. If you take this motor apart, it looks like pure copper, but it has an insulation on it. It's a varnish. It makes them go in a circle. The electrodes go in a circle to create an electromagnetic field. It's going around and around and around and around and around. But if we, instead of going around and around and around and around and around, if we just went, it wouldn't need to go around and around and around. It takes a shortcut, right, which is a bad thing. And if we overheat this winding, we end up taking a shortcut. I can just go here. It's a lot faster. And it don't work too good. So when we add capacitors like that, it increases the amperage. What happens when I put a smaller capacitor in? We put a smaller capacitor. What's going to happen overall?
Less electrons.
Less electrons, yes! Less electrons are moving! Less! Less electrons. So the capacitor is limiting It's limiting how many electrons go to that start winding. It's a limiting factor. It doesn't boost anything. It limits the flow. That's all it's doing, is limiting the flow. So if I put a bigger capacitor, it allows more electrons to flow. Smaller capacitor, small electrons to flow, which also affects the horsepower and some other things. But what if I have a compressor that somebody didn't pull a good vacuum, they left the moisture in the system, it turned to acid, which started eating away, causing leaks in the system, and now we got little pieces of copper floating around, and it wasn't enough to cause terminal blowout, but it started plating the bottom of all the moving parts of the compressor, and that compressor gets harder and harder to turn over time, right? What is it harder to start that motor? Yes. So what we could do is put in here a really big, giant capacitor, and that's going to allow a whole lot more electrons to flow, which is going to make the magnetic field stronger and more powerful, and it's going to give more torque and get that motor up to speed faster, right? But what happens when this motor is up to speed? What's happening now with this big, giant capacitor?
Too much.
Too much! Too much! Come on, man, it's too much! It's going to do what to the start winding?
Overheated.
Overheat it! Yes! It's going to melt the varnish off that winding. It's going to burn it up. It's going to be a bad
I'm washing
day.
my hands.
We need something to take this out of circuit.
If only we had a relay.
If only we had a relay. It would be relay good if we did. So what we're going to use is a potential relay. What's another word for potential?
Potential.
Potential. If I was to check right here, is there electrons flowing between these two terminals? Is there potential for electrons to flow between those two terminals? Yes, there's potential. So what's another word for potential?
Ability?
What's that?
The ability?
Ability, that's good. That's true. Ability is true. It is ability. That's right. No, you don't get a high five yet, but that's good. Ability. That's another word. So that's what I'm looking for. I love that you answered though. What's another word?
Starts with a V.
What? Volts. Volts! Volts! Mr. Volta come up with volts. So we have voltage. So this relay is called a voltage relay or a potential relay. Electromagnetic force, the push, the pressure. So what we use, remember we talked about this back EMF? We use this back EMF to energize a little electromagnet. That electromagnet is pulling a piece of metal. That piece of metal pulls these contacts that separates and takes this capacitor out of circuit, so it's not even there. When the motor slows down, what happens to my electromagnetic field here? Starts dropping. I lose that back EMF. Remember why? This is why capacitors are rated for a higher voltage, because that back EMF. I lose that back EMF. What happens to my electromagnetic field here? Goes away. What happens to my switch? It closes. It's ready for that next start cycle. But what happens if this capacitor fails? It failed. Electronically, it's not there. So we lose back EMF. This switch closes. What happens then?
It ain't happy.
It ain't happy. What happens?
Loud noises.
Loud noises. Okay. Maybe, maybe not. What's happening? What's going to happen if I lose my run capacitor? This motor slows down. First off, what's happening to my back EMF?
Going down.
Going down! Yes! Good! It's going down! It's going down, down, down. It's going down. So when I lose my back EMF, what's happening to my electromagnet?
Not energized.
Not energized. I'm losing my electromagnetic field. When I lose electromagnetic field, what's happening to the switch? Closes. So when the switch closes, is my start capacitor in circuit now? Yes, it actually becomes in circuit. So this slows down. This switch closes. We're sending, say, 200 something microfarads. Big plates! Big plates. We're energizing these plates. What's happening then to the start winding? Getting a boost. We got a lot of electrons flowing. We're getting a boost. That motor gets back up to speed. We get about 75% RPM. We create enough back electromagnetic force. What's happening now? Back electromagnetic force also means voltage, potential. What's happening next?
Running?
It is running, for sure. What else is happening?
It's dying?
Not necessarily, not yet.
It's not.
We get up to about above 75% of its full speed. What's happening?
The maximum amp draws or above amp draws.
We are getting above our amp draw that we need. That's good. That's good. What's happening?
That's starting to melt.
Not yet. What do you think's happening?
Is it above amp draw?
Well, we just know that we're at the 75% RPM. We now are creating an electromagnet. We're creating a generator in that start winding. What's happening next? Come on, I know you know it. What do you think's happening? What do you think's happening?
It's heating up.
It's heating up. Sure. I'm not talking about the start winding. That's we're creating electromagnet. What's happening?
Struggling.
What's happening specifically with that relay?
Well, it would eventually open, right?
Yes, because we now have voltage. Remember, it's a potential relay. It's a voltage relay. When we get up to 75% RPM, we're creating voltage. We energize our little electromagnet. What happens to the switch? It opens. The switch opens, but now the switch opens. Remember, we had a bad run capacitor. So what's going to happen to the speed of my motor?
It's coming down.
It's coming down off its high. It's coming down. It's like, now that my motor slows down, what's happening to my electromagnetic field here?
You're losing it.
I'm losing it. I'm losing it. I'm losing my electromagnetic field. What happens to my back EMF over here?
Drops.
Goes down. What happens to my switch?
It closes.
It closes. Now what's happening with my start capacitor?
It's back in circuit.
Back in circuit. Energized. Beat me up. It's energizing, right? We're back in circuit. So now we're taking this motor, and what's the speed of this motor doing?
Coming back.
Coming back up. Yes, get back on that high. 75% RPM. We're doing good. What's happening next?
Shut back off.
Well, it does, but what's happening to my back EMF? It's dropping. I'm losing my voltage. I'm losing my potential. What's happening to my electromagnet?
Dropping.
I'm losing it. I don't have enough voltage to keep the electromagnet going. What's happening to my switch?
Opening.
It's opening. Good. Is this in circuit now?
No.
No. What's happening to my motor?
Coming down.
It's coming back down. Coming off that high. Coming back down. When my RPMs drop, what's happening to my back EMF?
Goes up.
My back EMF goes up.
Comes down.
Comes down. It comes down. That's it. It's coming down off that high. It's coming down. We don't want to come down. It's coming down off that high. So we're coming down off that high. What's happening to my electromagnet? Right, my electromagnet loses. I no longer have electromagnetic field. What happens to my switch?
It closes again.
It closes again. What happens to my start capacitor?
I think we're saying the opposite. We
Oh.
went opposite. It opens.
Oh, I'm sorry. I was.
No, did we say it went? Or did we say it went down?
Went down.
It's going down.
We did.
I should have done my arrow.
I'm wrong.
So we close the switch, and then what's happening to my capacitor?
It's in circuit again.
It's in circuit. So what's happening to my RPMs now?
Back up.
It's going back up, back on the high. Just see a pattern here.
Yeah.
This is going to continue to happen until what?
The capacitor is replaced.
Until, well, yeah, that's true. But most likely before we get there, what else is going to happen?
Thermal knockup.
We're going to have one or two things going. We're going to either most likely burn out this start capacitor, so you're going to see it melting. Have you guys looked at the size of a start capacitor? You looked at the size of a run capacitor. You notice that the start capacitor is a lot of times smaller or the same size as the run capacitor, but the microfarads are way bigger because it's not made to stay in circuit the whole time. They use bigger, thicker plates. They use this big, thick, like tar type oil, and it's not made. It's plastic, so it's not made to dissipate heat. So what's happening is when we get this start capacitor hot by energizing it, those electrons in and out, 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 getting friction. We're getting heat. So this capacitor gets hot and it blows its guts all over the place. So anytime I see a start capacitor that's blowing its guts everywhere, my first thought is, well, we either have a bad run capacitor, thank you, or we have this relay welded its point shut and it's staying in circuit. What's the other thing that can cause it to fail? Back and forth, whole lot of amperage constantly over and over and over again.
It melts.
Yes, you can burn the varnish off that start winding.
Yeah.
Next thing you know, you have compressor. It's what we call unintended consequences of a start kit. Now, is there any product we can do that can help prevent in the case that would happen?
Probably.
Probably, yes.
Yeah, I think so.
Probably is right. There's a potential. Yes, what product could we install that would save if we had to have a start kit, what product could we add in there that could save all of this if our run capacitor did in fact fail?
Ooh, could we use the new AMRAD turbo capacitor that has a compressor protector terminal?
Yes! Absolutely right! The CPT terminal of that compressor, of that capacitor, you already installed those. That terminal will melt and it will take this out of circuit so that we don't lose the compressor. Alright, now you're like, well, what the heck is a CPT terminal? I'm asking this because I've seen people not know what it is. So we have that big old AMRAD capacitor, and look at the best way to draw it. We have the C for common power of the capacitor, same like the powers are unwinding. Okay. 10, 20, 30, 40, etc. So we power our capacitor, cool, no big deal. Now we have our all-in-one, big, cool start capacitor. We only need when we actually need it, and it's actually going to be an OEM, etc., etc., etc. So we have two wires, right? So we're going to just put one wire here. Where do I put the other wire? I got two wires. Where is this wire going to go?
CPT
What?
compressor protecting.
Yes! Yes! Two hands. Yes, absolutely right. The CPT terminal. What's the difference between the CPT terminal and the C terminal? What's the difference between those two? Go ahead and you don't know. It's okay. Say, I don't know. Tell me. What's the difference between the two?
I don't know, tell me.
Ah, yes! I'm so glad you asked! Absolutely! There is just simply a thin piece of metal right here. And the metal is made sacrificial metal. So if the amps get too high across this sacrificial metal, guess what it does? It sacrifices itself, bloop, and it saves everything. The CPT terminal. It's the same as the C terminal, except it just has a little sacrificial metal in there. It's sacrificial, it's not your son, it's not your firstborn, it's just simply a piece of metal. We can get rid of it, because obviously if that failed, we'd probably lost our capacitor in the first place. Cool, right? But now you see how we have the electrons equal on both sides, because it's going back and forth, back and forth, back and forth. So what if we see an older capacitor, and we put a hard start kit on there, and now it's working again? What do you think in your mind is what's happening? Hey, I put a start kit in, it's running, cool, I'm a hero, which is good, right? We like to be the hero. What else is going on? Think deeper. Hit, we talked about it already a little bit.
The compressor's struggling to start. So.
Why? It's obviously struggling to start because we're putting the start kit in to help it start, which is correct, it's not throwing you out, but yeah.
It's starting to lock up.
It is starting to lock up. Why?
Because it has shaving contaminants in it.
Could have shavings, could have contaminants. That's right. Specifically, what parts are we looking at having an issue? I keep going. I love the fact you're answering.
The rotor, right? Isn't.
The rotor. That's right. All of the moving parts. The bearings specifically. We talked about our compressor.
Anything with oil on it.
Anything with oil on it. That's exactly right. So there's going to be a few things that cause it. One is copper plating. You're going to hear people say, well, I never pulled a good vacuum, ain't never had a problem. And they're going to be like, oh, they don't make these compressors like they used to. If we don't pull a good vacuum, we have a copper plating. Copper coats all this, and it looks really cool. I got a whole bunch of them in my studio. Like, they look awesome. Horrible for the compressor, though. Copper plating makes these parts thicker and thicker and thicker. There's more metal, means less oil gets in there. It means it's harder to start. Now, one issue is somebody could have not pulled a good vacuum at the very beginning. We left acid, acid turns to, we left moisture, moisture turns to acid, good. So then acid starts causing, yep, all this starts eating away, and then that starts doing what to the moving parts? Copper plating makes them thicker, less oil, and then it gets harder and harder to start this motor. So then we're going to need more torque. How can I add more torque to get this motor started? Hard start kit, right? So it's not that the motor's like, oh, it's getting old, it's getting weak. No, it's not that. It's that something happened. Now, it could have been that they didn't pull a good vacuum at the beginning, but it could also be a leak, or it could have been to where somebody used their big old long 6-foot hoses. And back in my day, the longer the hoses you had, the cooler you were. Especially you had the nitrogen filled gauges. You were the coolest. Of course, nitrogen got everywhere and made a huge sticky mess, but you were still cool because you had the nitrogen filled gauges and you had the long hoses. You could sit in your truck and watch your pressures. What happens when those long hoses, we're hooking them up and taking them off? We're losing refrigerant, right? But contamination, moisture contamination. I see people bleed across the manifold and they never purge across the manifold. So they're literally pushing in contaminants into the system. That moisture can cause acid contamination. Another system that had acid, cross contamination. Also flood back. They get liquid into the suction line. We start washing the oil away. We start having compressor damage. We lose oil. It's all stuck in the evaporator coil or in the line set. We don't have lubricity. We start wearing away the bearings. The motor doesn't get weak. It's being killed. It's being murdered. So you're putting a start kit on there to help get it more life. The whole purpose, this whole big old long thing, was to think, if you have to put a start kit on to get the motor running, there should be a conversation saying, hey, there's already been damage to the system. You have a limited amount of time left on it. Right? It's not like, hey, we're putting this in and solving all your problems. There is a, just let the customer know, hey, there's a risk that we have, wear inside that compressor.
It's a pacemaker.
Yeah, I mean, you can get another, sometimes 10 years of extra life out of them. But a lot of times that's what it means. It could also mean you don't have enough voltage coming to it. Anybody check voltage at startup? For some reason, everybody wants to check inrush current, inrush current, inrush current. But I ask people, everybody that checks it, hey, what's your inrush voltage? I don't know. What happens when that motor starts up and what happens to this winding at startup? This winding right here. What do you think that winding is? There's no windings in this. When it's running, it's electromagnetic inductive load. But when it's not running, when we first electricity to it, what's this wire turn into?
Heater.
A heater! Yes! It's a heater! It's just simply a heater. And guess what a heater does?
Heats.
Gets hot, right? So you have a whole lot of amperage flowing through here. It's not until this motor gets up to speed that creates back electromagnetic force. You can take a magnet and drop it through a copper rod, which I have in the back, and it will slowly come out the other side. When we create electromagnetic field and we have this winding that's also now an induced magnet, it actually creates resistance. So when you first start the motor, you have more inrush of current. So you will naturally have inrush of current.
This is our first conversation. Inductive reactive circuits conversation.
The difference is, if we have our lines or wire coming to the motor and they're super long, or they're going through, bad connections, by the time they actually get to the point where we need that voltage, what could happen to our voltage? We could lose our voltage. Our voltage could drop. The lower voltage we have, the longer it takes this capacitor to start up, or the longer it takes the motor to start up. And that's where you'll see sometimes the lights will be dimming because we have a voltage drop. So what I care more about than inrush and startup inrush current is I want to see what the voltage is when that compressor starts up. If that voltage drops too low, sometimes you'll have to find where it is. Bad disconnects all the time. I've seen bad breakers all the time. I've seen where somebody replaced the system. The new system's now doing the same thing. Went back and found a bad breaker. I'm not saying you should open up breaker panels and check all that, but it needs to be like in your thought process, in your mind.
So we had a CubeSmart in Jacksonville that had all the condensers on the roof, and it was a 208 application. Okay, a lot of commercial buildings are. This building is a 208 application. Do you guys know what that means, a 208 application? That means you're just using 2 legs of 3-phase and a Y transformer. So you don't get what we normally get in residential houses where we're pushing 250 volts in most cases. You're going to get 220, something like that. It's not actually 208, but it's going to be much lower. Now you combine that with really long electrical wires, and you will have more voltage drop. We had a store that essentially every single unit, the compressors would only start like 1 out of 3 times because of the voltage drop that existed. And it was that way from the very beginning. We didn't install the units, but we were going in trying to troubleshoot, and we were seeing failures and other issues. And so that was a case where, because of the long line, they were supposed to have factory hard start kits on them anyway. So when you looked at the long line, that was actually part of the specification. They were supposed to have them anyway. And because of the lower voltage plus the long line, long electrical lines, they weren't starting. But keep this in mind: if you have a residential AC unit, Is it rated for, what voltage is it rated for? I'll just ask you guys a question. Do you know what voltage a typical residential unit is rated for?
230.
But it's between 290.
It's rated for 230 volts, actually. Okay, it's a weird thing, but we're typically using the higher end. But it's also rated all the way down to, I think, 197 volts,
That sounds right.
which means that it's rated to work on a 208 structure. But when you decrease the voltage, you're decreasing the pressure, you're decreasing the electromagnetic fields, everything. Do we swap, whenever we install them on a commercial building, we swap the capacitors out to compensate for that, right? No, we do, right? Of course not. Of course we don't. There's not even a spec for that, right? But do you think those capacitors are perfectly sized for both applications? No, they're not, right? So they're just making it kind of in the middle, and it's sort of a catch-all. When you're on the lower range plus long wires, it's going to be more likely to have systems that aren't starting, and it's going to be more likely that a hard start's actually appropriate. Does that make sense? All right, so the point of this is not to demoralize you, because I saw your faces when he's going on about all this stuff, and it starts to feel very complicated. It's not very complicated. It's just once you get these little seeds of information, it's going to open up a whole new world of what's actually happening. All of you have cartoons in your head. This is a term Nathan and I have always used. You all have cartoons in your head that get you through the day. You know how to fix most problems. But the problem is a lot of the cartoons in your head are wrong. And if you can swap the cartoon that's in your head with a new one about how it actually works that's better, you're going to be a better tech. And that's all we're doing. Because even the language we're using about electrons moving in and out of the wires and everything, when you get to the next layer, even all that kind of falls apart. And then you get to quantum physics and everything falls apart, right?
That's so true.
The best you can do is have the most functional, when I say cartoon in your head, you know what I'm talking about, right? Like you imagine how it works on the inside. And the more you can see the inside of a compressor, well now your cartoon's a little better. Because now you know what it looks like and you know what you're actually trying to lubricate, right? And you know what happens if you leach copper. So that's what we're trying to accomplish here.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community, for techs, by techs.